Now, in some questions, you'll find it is very difficult to identify any pattern. And for those functions, you may not even find basic values f0, f1. There we may use two concepts from functions that can come to our rescue. And the tools are injectivity, that is, we'll check if the function is 1, 1, and surjectivity, that is, the function is on 2. So if we can prove injectivity, then if we ever get this condition in functional equation that fa equals fb, from there we can straight away get a equals b, and it may unlock many doors for us. So with injectivity and comparing functions, either this question it changed to algebraic structure, or for functions with compositions, it'll give you some simplified structures. Now this single move is responsible for solving a large number of Olympiad level functional equation questions. So if a function is defined from D to R and it is injective, if fa equals fb, it implies a equals b for all ab belongs to its domain, which means distinct inputs will give you distinct outputs. Now in the problem, generally it is not given that this function is injective. So this condition, it must be derived from the functional equation itself before you can use injectivity. So basically there are three routes. One is you are given directly that the function is injective, or it is a bijection. Second route is through strict monotonicity. So if we can show this f is either strictly increasing or strictly decreasing through calculus or from any inequality embedded in the system, then we can clearly say if a is less than b, then fa will be less than fb. So the second route is through strict monotonicity. And the third route is using the composition lemma. Now this lemma says if hx is g of fx and this function h is injective, then this f is injective. So generally you'll find these type of problems in Olympiad functional equations. Now injectivity, it gives you this right of cancelling this function f to deduce a equals b. Then this surjectivity, it lets you choose what goes into f. So if you have any target value in mind, say y0, which belongs to its codomain, then if it is surjective, you'll surely have some x0 where fx0 is equal to y0. In most of the cases, you'll need a point where you'll show there's a point such that fx0 is 0, because 0, it simplifies a lot of problems. So here you'll have to prove this 0, it belongs to the range of this function. So a function defined from D to Y is surjective if for every y belongs to y, there exists x belongs to D such that fx is equal to y. And here also you'll need dual composition lemma. So if hx, which is gfx, is surjective onto y, then this g is surjective onto y. So injectivity forces inner function to be injective, whereas surjectivity forces this outer function to be surjective. Now let us look at it through examples. Suppose we are given this function f, which is defined on R to R, and it says this f x plus fy, it is fx plus y for all xy belongs to R. If we substitute x equals 0 in this, we'll get f of fy, it is f0 plus y for all y belongs to R. Now this right hand side, it is a linear function. And because it is a linear function, it is strictly increasing. And if it is strictly increasing, this f of fy will be one function. And through composition lemma, it will give us this f, it is injective. And for this question again, if you look at f0 plus y, this f0 plus y is a linear function. So its range will be all real numbers. And through composition lemma, again we can say this f, it is surjective. So from this simple equation, we have deduced this function, it is a bijection. And now we can use these conditions to find this function fx. So let fa equals fb. Now in this given equation, if we put y as a, we can write f x plus fa equals fx plus a. And if we put y as b, we'll get fx plus fb equals fx plus b. Now since fa equals fb, both of them they'll be same. So from here we'll get fx plus a will be equal to fx plus b, or simply a equals b, which shows this function is injective. Now in the second part, we need to find this function f. So let us say there is a point C in R such that fc is 0. So in the equation, if we put y as c, we'll get fx plus fc, and it'll be equal to fx plus c. Now fx equals fx plus c implies c is 0. So we'll get this condition that f0, it is equal to 0. Now in the given equation, if we put x as 0, we'll get this condition that f of fy will be equal to y. Now we can write f of fy equals fx plus y, and we'll let fy as some variable t. Then we can write f of fy will be ft, and f of fy is y. So we can write ft equals y. So this equation, it reduces to fx plus t equals fx plus ft, which is Cauchy's equation. And since we are given this condition of continuity, that means we'll get this solution fx equals ax. Now we can also find the value of a because we know f of fy equals y. So a of ay will be equal to y. That is, value of a will be either plus 1 or minus 1. So this function fx will be either plus x or minus x, and that is the answer to this question. So let us take another example. Now the second example, we have to show f is injective and we have to find f0. So this function f, it is defined on R to R satisfying fx cube plus fx. This is equal to x. For all x belongs to R. Now to prove injectivity, we'll let fa equals fb and it is equal to say some value k. Then k cube plus k will be fa cube plus fa and will be equal to fb cube plus fb. Now fx cube plus fx is nothing but x. So this is a and this is nothing but b. So from here we can clearly say this f is injective. Now this fx, it's actually inverse of this function phi t equals t cube plus t, because phi of fx will be fx cube plus fx, which is simply x. And if we differentiate this, then phi dash t is t square plus 1. It is greater than 0, which is strictly increasing. And since it is cubic and strictly increasing, this phi is bijection. So this f, it is phi inverse and is also well defined. Now phi 0 is 0. That means f0 is also 0. So this is your second example where we have established injectivity through the given functional equation. Let's take third example. Suppose a function is defined on R to R satisfying f of fx equals x plus 6. Now clearly it is linear, so it is strictly increasing. And therefore this f, it is a bijection. Today we'll solve this beautiful functional equation question, which is going to teach you a lot of things. Now in this question, we are given that a function is defined on R to R such that fx plus fz plus fy is equal to zfx plus y for all xyz belongs to R. We need to prove that this function is fx equals x. Now this seems a complicated function because here we have three variables. Also, there is a composition f of x, fz plus fy, and we are not given any initial values to work with. So we cannot straight away find f0 or f1. So what to do in such situations? Now, since we do not have anything to extract from this equation, the first instinct should be, what global properties can I extract from this function before I can begin my substitution? And for that, my first step would be to check bijection. And since we already know fx is going to be x, so it must follow bijection. Now with bijection, we are going to achieve two things. First is, if suppose we have fp equals fq, and we know since it is 1, 1, we'll say p equals q. And with surjectivity, we know that this range of function fx, it is going to be all real numbers. And if fx belongs to R, then there exists a unique point A such that f is 0. So this is our starting point. So in order to find a way ahead, we'll first prove bijection. Now we'll begin with injectivity. So we'll prove function is injective. And for this, let's say we have 2 points, fa equals fb. Now if we fix x and z, then we can write x fz plus fa will be equal to x fz plus fb. So we have basically added x fz both sides. And if we take function both sides, then we can write fx fz plus fa will be equal to fx fz plus fb. Now this is equal to z fx plus y. So it will be equal to z fx plus a, and here it will be equal to z fx plus b. So the only condition that we get from here is a equals b. So if fa equals fb, then a equals to b. That means this function f, it is a 1-1 function. So we have proved injectivity for this function. Now we'll come to surjectivity. Now we are given that this function f x fz plus y, it is equal to z fx plus y for all xyz belongs to R. Now if we fix xz, so we have fixed this term. Now here right hand side, y is going to take all the values from minus infinite to plus infinite since y belongs to R. So this RHS, it'll take all real values. Basically this right hand side, it defines the values this function can take. So this function has a range R, and since range and codomain are same, that means this function is an onto function. So now we can say our function is both 1-1 and onto, and hence it is a bijective function. So now at least we have something to work with. Now once we have proved bijection, what we'll do is we'll try and find a point where fx is 0. So we know that this function f, it is 1-1 and onto. So there'll be a unique point C in R such that f C is 0. Now here we'll achieve two things. First, we'll try and prove C is 0. So that is f0 equals 0. And also we'll try to find out some functional relationship in one variable. And we'll try y because y looks neat. So what we'll do is we'll put x as C and z as C. So we'll get f CFC plus fy, it is CFC plus y. Now fc is 0, so this is 0 and this is 0. So from here we can write f of fy will be equal to y for all y belongs to R. That means f is an involution. Now using this involution, we'll try and prove f0 is 0. And for that, what we'll do is, in this given equation, we'll put x as 0 and z as C. So we'll get f of fy will be equal to CF0 plus y, but we know that f of fy is y. So from here we'll get C into f0 is 0. So either C is 0 or f0 is 0. If C is 0, f0 is 0. So both the things, they imply f0, it is equal to 0. So first we have proved bijection, and then using that we have proved that f0 is 0. Now using this, third step is going to be, we'll prove that this f is multiplicative. So we just need to prove fxy equals fx into fy. And for this, what we'll do is, in this given equation, we'll put y as 0. And if we put y as 0, we'll get f x fz, it is equal to zfx. And since this function is a bijection, what we'll do is, we can replace z with fz. So we can write fx, f of fz will be fz into fx. Now f of fz will be simply z. So from here we can write fxz, it is fx into fz. That is, our equation is multiplicative. Now we can use this multiplicative equation to find the value of f1. So what we'll do is, we'll put x as 1 and z as 1. We'll get f1 equals f1 square. So either f1 is 0 or f1 is 1. But since f0 is 0 and is a 1-1 function, so f1 cannot be 0. So the only option that we have here is f1 equals 1. So we get this condition that f1 is equal to 1. And we also have f of fy, it is y for all y belongs to R. Now, fifth is, we'll try and prove f is additive. So basically, this function is a Cauchy's equation. So essentially, we need to prove fx plus fy, it is fx plus y. Now, looking at this structure, we have x fz plus fy and fx plus y. So what we'll do is, we'll put x as 1. So we'll get f of fz plus fy, and this is z f1 plus y, and f1 is 1. So we'll have f of fz plus fy will be z plus y. Now we need fx plus y, which we can have from here. And we also know that composition of f with f, it is involution. So f of fy will be simply y. So what we'll do is, we'll take f both sides. Now f of fx is simply x. So this left hand side will be fz plus fy. It is f z plus y for all yz belongs to R. That means this function is additive and it is a Cauchy's equation. We have proved it is a Cauchy's equation, but then there's no regularity given in the question. And without regularity, we can say that at best, fq is some kq where q is a rational number. We cannot say it for all real numbers. So we need to assert regularity. So next step obviously would be we need to assert regularity so that we can say fx equals ax for all x belongs to R. And in order to assert regularity, what we'll do is we'll prove that this function f, it is monotonic. Now we know that from f1 equals to 1 and Cauchy's equation, we can say fq will be q for all rational numbers, and for any t which is greater than or equal to 0, we can write this t as under root t square. So what we'll do is we'll use multiplicativity to prove that this function, it maps non-negatives to non-negatives. So we can write ft as f under root t into under root t, and it'll be f root t square. And since this is square of this real function, it'll be always greater than or equal to 0, which implies this f, it maps non-negatives to non-negatives. Now what we'll do is we'll assume let a be greater than or equal to b. Then we can write a minus b is greater than or equal to 0. Now from additivity, we can write f a minus b will be equal to f a minus f b, and since f, it is greater than or equal to 0, so it will be greater than or equal to 0. That means f a is greater than or equal to f b. So if a is greater than or equal to b, then f a is greater than or equal to f b. That means this function is non-decreasing, or it is a monotone. So now we have asserted regularity using monotonicity. So now we have Cauchy's additive equation with regularity. We can say that this fx is of the form kx for all x belongs to R. Now since f1 is 1, that means k is 1. So this function fx will be simply x. And that is what we need to prove in this question. So this question, it involved injectivity, surjectivity, multiplicativity, additivity, involution, Cauchy's equation, monotonicity, and using all that, we were able to prove fx equals x. So I hope you have learned a few things through this elegant question. Here the question is, find all functions defined on R2R such that f minus x equals minus fx. So basically it's an odd function, and we put x as 0, we'll get f0 equals 0. So that's your first condition. Your second condition is fx plus 1, it is fx plus 1 for all real x. And this third condition is f1 by x it is fx upon x square for all x unequal to 0. Now f0 is 0. In this second equation, if we put x as 0, we'll get f1 equals f0 plus 1, which means f1 is simply 1. And for any x which is a natural number, then this fn plus 1 will be simply fn plus 1. So basically it'll be an AP. So fn plus 1 minus fn equals 1 with a common difference 1. So f1 will be 1, f2 will be 2, and fn will be n. But we need to find this function for all real x. So what we'll do is we'll take this equation B and we'll replace x with 1 by x. We can write f 1 by x plus 1 will be f 1 by x plus 1, and from C f 1 by x is fx upon x square. So it will be fx upon x square plus 1, or simply fx plus x square upon x square. And this is f1 plus x upon x. Now what we'll do is we'll try and generate this f1 plus x upon x using this equation C by replacing x with x upon 1 plus x. So in this equation C, if we replace x with x upon 1 plus x, it'll be this f1 upon x upon 1 plus x, and it'll be this fx, which is f x upon 1 plus x upon x upon 1 plus x whole square. Now this is f1 plus x upon x. Now we can write this as plus 1 minus 1. So it'll be this f1 minus 1 upon 1 plus x. And this is x square upon 1 plus x square. And we know that f1 plus x is fx plus 1. So it'll be this 1 plus f, and it'll be this minus 1 upon 1 plus x upon x square upon 1 plus x whole square. Now we are also given this fx, it is an odd function. So f minus x will be minus fx. So we can write f1 plus x upon x will be 1 minus f 1 upon 1 plus x upon x square 1 plus x whole square. Now this again is your third equation, f1 by x, and will be fx upon x square. So we can write this as 1 minus, and f1 upon x is fx upon x square. So it will be this f1 plus x upon 1 plus x square upon x square 1 plus x whole square. So it will be 1 plus x square minus, now f1 plus x is 1 plus fx. So it will be minus 1 minus fx upon x square. Now these two left hand side, they are same. So we'll compare the right hand side to get our function fx. So it will be fx plus x square upon x square will be equal to 1 plus x square minus 1 minus fx upon x square. Now this x square will cancel, 1 plus x square will cancel. So we'll get 2fx equals 2x, or simply this function fx will be equal to x. So for these given conditions, your function fx is defined as simply x. Now here the questions. Find all pair of functions f and g defined on R to R such that A, G is 1, 1, and B, F, Gx plus Y equals G, X plus Fy. Now in this, if we put y as 0, we'll get f of gx will be g x plus f0. And here, if we put y as g0, we'll get f gx plus g0 will be g of x plus f of g0. Now, f of g0 will be g of f0. And in this equation, if we put x as 0 and y as gx, we get f g0 plus gx will be this g 0 plus f of gx. So we can compare these two. Then we can get g x plus f g0 will be equal to g of f gx, and f gx is g x plus f0. So it will be g of g x plus f0. Now, since it is a 1-1 function, we'll get g x plus f0 as x plus f g0. Now, let us take x plus f0 as u. So it will be this gu, and we can write x as u minus f0 plus f g0, which is basically some constant. So from here we can say gx is of the form x plus a. So your gx is x plus a. Now we have to find fx. So we'll substitute gx here. So we'll get fx plus a will be x plus f0 plus a. Now x plus a is v, so it will be fv equals v plus f0, which is some constant, or we'll get fx as some x plus b. So both the functions fx and gx, they'll be linear functions with leading coefficient 1. Sometimes you'll get a question where you'll be not given functional equation. Say, for example, you may be given fx plus y is less than equal to fx plus fy, which is subadditive, or maybe this inequality fx plus y by 2 is less than equal to fx plus fy by 2, which is midpoint convex. Now in such questions, there are two pathways. Either you'll get an exact function using sandwich principle, so if you can derive fx is some greater than equal to phi x from one direction, and then from other direction you can derive fx is less than equal to phi x, then from sandwich theorem we can say this fx is exactly phi x. So this is one pathway, and the second pathway is from the inequality you can infer monotonicity or boundedness, which can give you the condition of regularity needed to rule out wide solutions on Hamel basis. Now in this question we are given that if f satisfies fx plus y is less than equal to fx plus fy for all xy, and also fx is less than equal to x for all real x, find this function f. Now, from the second condition, we can write f0 will be less than or equal to 0. And in this first condition, if we put xy as 0, we'll get f0 as greater than or equal to 0. That means both the conditions, they can only be true if f0 is 0. Now we'll try and use this. For this first inequality, we'll put y as minus x. We'll get f0 will be less than or equal to fx plus f minus x, or simply fx plus f minus x will be greater than or equal to 0. Now we can write fx will be greater than or equal to minus of f minus x, and from the second one we can write f minus x will be less than or equal to minus x, or minus f of minus x will be greater than or equal to x. So it will be greater than or equal to x. So we'll get this condition that fx will be greater than or equal to x. But we are given that fx is less than or equal to x. That means the only condition possible here is fx equals x. So the function which satisfies the two given inequality is fx equals x. So here the question is, find all f from n to n such that f2 equals to and fmn, it is equal to fm into fn for all coprimes mn. So that means GCD of mn, it should be 1, and fm is always less than fn whenever m is less than n. Now, if we put m and n as both 1, then we'll get f1 equals f1 square. So either f1 is 0 or f1 is 1. And since codomain is natural numbers, it cannot be 0. So f1 is 1. Now we're given f2 as 2. Now we can write f6 as f2 into f3, and f2 is 2, so it'll be 2f3. Now we know that 2 is less than 3, is less than 4, is less than 5, and is less than 6. So f2, which is 2, will be less than f3, and it'll be less than f4, which is less than f5, and it'll be less than f6, which is 2 times f3. Now there are strictly 3 increasing natural numbers between 2 and 2 times f3. Now this forces f3 equals 3, f4 equals 4, f5 equals 5, and f6 equals 6. So we guess this fk, it must be k for all k belongs to n. Now we prove it using strong induction. So our first case, P1. Now F1 is 1. This is true. Second is Pn be true, or all the cases from P1, P2, Pn, they are true. That is, any Pk will be equal to k when k is less than or equal to n. Now we choose a convenient coprime pair, and we know that 2 consecutive numbers are always coprime. So f n minus 1 into n will be f n minus 1 into fn, which is n minus 1 into n Now we know that n is less than n plus 1. It is less than n plus 2. And it'll be less than n minus 1. Or fn will be less than fn plus 1, fn plus 2, and this is fn into n minus 1. Now fn is n, fn into n minus 1 is n into n minus 1. Now the function before this will be f n square minus n minus 1. So total number of functions in between these two functions will be n square minus 2n minus 1. And if we look at gaps between these two natural numbers, it will be n square minus n, and then minus n minus 1 will also be n square minus 2n minus 1. So for it to be an increasing function, there will be exactly a gap of 1, because more than one gap is not possible in this structure. So from here we can say f n plus 1 will be equal to n plus 1. That means p n plus 1 is true, and therefore from induction we can say f n will be equal to n. Now the question is, let f be a function defined from 1 to infinite to 1 to infinite, satisfying these two conditions. And the first condition is fx is less than equal to 2 1 plus x for all x belongs to its domain. And second condition is x f x plus 1, it is fx square minus 1 for all x belongs to 1 to infinite. Now we need to prove that fx is less than equal to x plus 1. Now from this condition B we can write fx square, it will be x into fx plus 1 plus 1. Now from this first we can write fx plus 1 will be less than 2 into 2 plus x. So it will be less than or equal to x into 2 plus x plus 1, which is 2x square plus 4x plus 1. Now if we add 1 and subtract 1, it will be 2 into x plus 1 whole square. So it will be less than 2 into x plus 1 square. Or we can simply write fx will be less than root 2 x plus 1. Now we'll use this fresh bound instead of this a, and again we'll use this argument. So again we can write fx square, it is xf x plus 1 plus 1. Now it'll be less than x into, now fx plus 1 will be less than root 2 x plus 2 plus 1, which is root 2 x square plus 2 root 2x plus 1. Now we can add root 2 and subtract root 2. So it'll be less than root 2 x plus 1 square, because 1 minus root 2 is a negative number. So from here we'll get another bound, fx is less than 2 to the power 1 by 4 x plus 1. So if we keep applying these iterations, we'll get fx should be less than 2 to the power 1 by 2 x plus 1. Then we got fx less than 2 to the power 1 by 4 x plus 1. And then we can get fx will be less than 2 to the power 1 upon 2 to the power n x plus 1 for all n belongs to natural numbers. Now as n increases, 1 upon 2 to the power n, it approaches 0. So clearly this fx will be less than x plus 1, which is what we need to prove in this question. Now the question is, let f be a function defined on R to R such that f3 is 1 for all x belongs to R. Fx plus 3 is greater than or equal to fx plus 3 and fx plus 1 is less than or equal to fx plus 1, and says put gx as fx minus x plus 1. We need to find the value of G 2008. Now, from this first equation, we see fx plus 3 minus fx will be greater than or equal to 3. Now, from this second one, we can write fx plus 2 will be less than fx plus 1, which will be less than fx plus 2, and in the same way fx plus 3 will be less than fx plus 1 plus 2, which is less than fx plus 3. So from this second condition, we'll get this inequality fx plus 3 minus fx is less than or equal to 3. Now, both of them, they can be simultaneously true if and only if fx plus 3 minus fx, it is equal to 3. So this is the equation we have. Now in the question it is given that f3 is 1. And since this is an equality, that means all the conditions given in the question, they'll also hold. So we'll get fx plus 1, it should be equals to fx plus 1. Now we are given gx equals fx minus x plus 1. We can write gx plus 1 as fx plus 1 minus x plus 1 plus 1. Now fx plus 1 is fx plus 1. So it will be this fx plus 1 minus x, and which is nothing but gx. So this function gx, it's periodic with period 1. Now we need to find G 2008, and we know that we can write this as G3 plus 2005. Its period is 1. So it'll be equal to G3, and G3 is F3 minus 3 plus 1, and F3 is 1. So value of G 2008 is minus 1. And that is the answer to this question.